Hi, everyone, and welcome to this OpticStudio webinar. Today, we'll be talking about how to accelerate your tolerance analysis. My name is Kristen Norton, and I will be your host. So, this webinar will discuss tips and tricks for speeding up your OpticStudio tolerance analysis. We'll start with a very brief overview of tolerancing in OpticStudio. If you are new to tolerancing, this will be a lot of information all at once. So if at the end of the webinar you are looking for more information, I would recommend that you go to our website, zmax.com, click on Optic Studio, then go to the resources menu and click on knowledge base. Once you're there, you will see a screen that looks like this image here. If you click on tolerancing, you will see all of the knowledge base articles that are directly related to tolerancing. If you want a more comprehensive overview, then I would recommend checking out our newly redesigned courses. There are two, which include tolerancing content. The first course I have listed here, Optical System Design, is an introductory course. And so the tolerancing content is more introductory there, but it's a nice overview of everything that you can do with the tolerancing features in OpticStudio. The next course I have listed here, or boxed, is the Advanced Optical System Design. And this includes more detailed information about tolerance analyses and how to tolerance more advanced optical systems. So today we will start with the tolerancing overview and then talk about two different categories of choices and features that can be used to speed up your tolerance analysis. In the engineering choices, we will first talk about the idea of intelligent design and then how you can use the tolerancing evolution to your advantage. There are then three OpticStudio features that we will cover. There's the Paraxial focus compensation, then the tolerancing cache, and then polynomial sensitivity. So let's start with the tolerancing overview. So tolerancing is about accounting for manufacturing error so that the as-built design meets its intended specification. And there are three different tolerancing capabilities inside of OpticStudio. We have a sensitivity tolerance analysis, which lets you see how known tolerances will change your system. Then we have an inverse sensitivity analysis, which works in the other direction, and it lets OpticStudio calculate the tolerances for you. And then the Monte Carlo tolerance analysis can be used to simulate the effect of all of the tolerances simultaneously. So now let's talk about a typical tolerancing process. So you start by defining an appropriate set of tolerances for your lens or for your optical system. Usually the default tolerances, which are generated using our tolerancing wizard, are a good starting point. And then you'll want to modify some of these defaults to meet the needs of the specific system that you have. And then you need to add in compensators. Okay? And compensators represent what you will be adjusting to improve system performance and to compensate for the manufacturing defects. Then you select the criterion or what will be measured as system performance. And this could be RMS spot size, wavefront error, MTF, bore sight error, etc. And then you'll select the desired tolerance mode, meaning sensitivity, inverse sensitivity, or straight to the Monte Carlo simulations. After that, you perform the selected tolerance analysis, and this could take quite a while. And then in the last step, you review your tolerance data and then repeat as necessary. Okay. You should expect to repeat this process over and over again as your design matures. So tolerancing is, by its very nature, an extremely detail-oriented and time-consuming process. In fact, the tolerance analysis can be one of the most time-consuming aspects of the design process and can take longer than all of the other stages combined. Okay. There are a number of strategies, though, that can be used to reduce the time taken and the computation effort needed to complete this. Okay, some of these are simply just sensible design and engineering choices, and others are features that we've added into OpticStudio specifically to help reduce the computational complexity. Okay, so we'll start by talking about these engineering choices. Okay. And so our first suggestion is to not use automatic optimization cycles. Okay. So this cycles setting determines how rigorously OpticStudio will attempt to optimize the compensator values. So whatever you have set to be a compensator will essentially be a variable which gets optimized. And if this is set to automatic, then OpticStudio will call the optimizer in auto mode, which will run the optimizer until the optimization of all the compensators has converged. If the compensators are difficult to optimize, then higher setting here or automatic may really increase system performance. Okay, but it also could be overly optimistic because you need to think about how many iterations will be performed during system alignment. Okay. Now, on the other hand, if too few optimization cycles are selected, then the tolerances will be pessimistic. So the predicted performance here will be worse than the actual performance. So what you need to remember is that the optimization stage for which you are setting the cycles here, okay, this simulates a shop floor or a user adjustment. For example, focusing a projector onto a screen. Okay. In this case, it's not necessary to reduce the spot to the last picometer, okay, but 3 or 4 cycles of optimization are usually all that's needed. And the next recommendation is to use as few configurations and wavelengths and field points as are necessary. Okay. And this is not necessarily the same number that was needed to optimize in the first place. Okay. We recommend that you try to identify the worst case and then tolerance that. So there are 3 different settings you can use to define your field points in a tolerance analysis. There's Y-symmetric, which means you have field points along the y-axis only. There's XY symmetric, which means you have field points along the x and y axes. And then you can also select user defined, okay, which means it will use whatever field definitions exist in your current lens file. But as I said, the field definitions that you used for optimization and other analysis may be inadequate for tolerancing. So take, for example, a rotationally symmetric lens that used field definitions of 0, 7 degrees, and 10 degrees. Okay. If you then need to tolerance a lens element or a surface for decenters in x and y, okay, this will then break that symmetry. Okay, so you will need more or different fields than just those that you had before along a single axis. But more field points mean more calculations. And so this means, an increased computation time. So there are ways to include these tolerances, though without increasing the number of field points, if you are smart about it. Okay, so for example, say again the nominal design is rotationally symmetric. Well, we could try to align all of the tilts and decenters that we need for tolerance values, and we can align them all so that the worst case is just along the y-axis. And then we only need to use y-symmetric fields instead of x and y. And the next suggestion is to remove the weak tolerances. So, for example, say you are using TIND to tolerance the index value. Okay? But if this has a very minor effect on your system performance, then it can be removed in the early stages. Okay? Another thing to consider is if you are using TIND and TABB, but they are very weak, okay, then you may not need to use more than one wavelength. Okay. Remember, more wavelengths means more data points for computation and will significantly increase your computation time. Okay. So the sensitivity tolerance analysis will show the effect of each tolerance on the criterion. So it should be easy to distinguish which operands or tolerances have the largest effect on your system performance. Okay. But if you wanted to investigate further, you can use a save operand in the tolerance data editor. So I will show you an example. I'm going to open up a file that's very similar to the original Cook triplet. Okay. Here, if I open up a 3D layout, okay, you'll see we have 1, 2, 3 lenses. Okay. And let's say you wanted to tolerance the index and OBI number tolerances for the glass at this first lens. Okay. If we look in the lens data editor, this is surface 1 and the material is SK16. So in my tolerance data editor, I have two operands, okay, which use the default tolerances for the index and OBI numbers. And after each of these operands, I have an additional save operand, okay, with different file numbers. Okay. So this save operand will save the files which were created to evaluate the tolerance operands at their minimum and maximum tolerance values. Okay. So this means that you can open up the file which actually shows the index at its extreme value, and you can use all of the analyses to compare the data from that file to its original. So I ran a tolerance analysis, very quick one with this, and I will show you one of the files that was created. So here you can see that we have an offset solve applied to the material. So the index offset was set here. Okay, so the tolerance value was just plugged into this solve. And now if I needed to, I could go back and look at any of the analyses here in this tab and compare them to the nominal file as well. So this screenshot is just showing here now how the offset solve was used to tolerance both the index and the OBI numbers. The next suggestion is to change your strategy as the design evolves. Okay. So remember that just like with optimizing, as your design matures, you can also change your strategy. So early in the process, you'll focus on the worst case scenarios just so that your design gets into the right ballpark. And then you can add more detail as your confidence in the design candidate grows. So you can run the final tolerance analysis with all of the needed tolerance operands, all the wavelengths, all the configurations, etc. Okay. But you should only invest the time this will take once you have some reasonable degree of confidence that the design is going to pass the test. Okay. Otherwise, you'll have to do it all over again. Now, that said, OpticStudio does have some built-in tools which will help improve your tolerance analysis speed. And three of those tools are the Paraxial focus compensation, the tolerance in cache, and polynomial sensitivity. So we'll start by talking about how Paraxial focus compensation works. So this works by ignoring all the other compensators you may have defined, and instead it defines only a back focus compensator. Okay, so this mode does not use rigorous optimization of the back focus, but instead it splits the last thickness into two surfaces. The first is a surface with a paraxial image height solve, which moves you to the paraxial image plane. And this is the bulk of the backfocal distance. But this paraxial image height solve is implemented with what we call a marginal ray height solve. And you can plug in settings such that it will be solving for when the paraxial marginal ray has a height of 0 or when it crosses the optical axis. Then the second surface is a refocus surface that moves you back to the real image plane. This is a small correction factor. It means that the focus is adjusted to maintain the same amount of defocus that was in the nominal design, but without attempting to re-optimize the back focus. Uh, During tolerancing, the paraxial marginal ray solve will automatically update to keep the design at paraxial focus at the surface just before the last surface. Then the constant refocus thickness is applied to the final thickness. And the speed advantage is that no cycles of optimization are required. And there's only one ray that is needed to be traced in order to update the paraxial height solve. So the pictures here show a multi-configuration system. In the layout on the right, you can see that the blue rays represent the first configuration, and this first configuration ignores surface 7. Then the green rays represent configuration 2, which ignores surface 6, and that's the grayed out surface. Surface 6 has a thickness which puts the image plane at the best location for the smallest RMS spot size, and surface 7 uses a marginal ray height solve instead. Okay, so this solves for the paraxial image plane location. And in this case, you can clearly see that the paraxial image plane is beyond the real focus location. So we would need a defocus of about 0.2 millimeters to return to the configuration 1 image plane position at the smallest spot size. And this is essentially what paraxial focus compensation does during a tolerance analysis. Okay. And I can show you this with a quick example too. So this is again the Cook triplet, okay, but we can see here the image thickness starts at 42.22 millimeters. And we know this is in millimeters. If you look in the System Explorer, in the unit section, we're in millimeters. So this thickness was found using the Quick Focus tool. Okay. So this is in the Optimize tab, Quick Focus. And if we're looking for the smallest spot size, we'll select Spot Size Radial with a centroid reference. Okay. And that adjusts the last thickness here. Now here, let's see how it changes if I instead add a marginal ray height solve. A height of 0 means it will solve for the thickness where the ray height intersects the optical axis, and a pupil zone of 0 specifies that we are using a paraxial ray, not a real ray. So you can see the thickness increased to about 42.415 millimeters. We can refocus this with an additional surface thickness. So all I need to do is click on the image plane, press the Insert key, and I can run the Quick Focus tool again. So this gave us a defocus of about 0.19 millimeters, okay, back to our original image plane location. And so these are the two surfaces that would be added if we were using paraxial focus as a compensator in a tolerance analysis. So if we try perturbing any of these other lens parameters, my marginal ray height solve will automatically update, but this defocus value will stay constant. There are two extreme cases when you can use paraxial focus as the compensator in a tolerance analysis. And the first is in systems which have relatively poor target performances and coarse tolerances. And in particular, if you are looking at radii and thickness tolerances, okay, these perturbations can be easily compensated by a focal shift. Then at the other end of the spectrum, okay, The paraxial focus compensator can also be used in exquisitely well-balanced systems with very tight tolerances. Okay. This is a little counterintuitive, but when a system is very well corrected, it performs close to its paraxial performance. And so the tight tolerances will have only a first order effect. But paraxial compensation should not be relied on for final system evaluation. Its purpose is really just to give you a fast first cut in these two extreme cases. Okay, the next feature that we're going to talk about now is the tolerancing cache. So the first time a tolerance analysis is run, all the tolerances are perturbed, um, and the perturbed criteria are evaluated and then saved in memory. Then this cached data can be used to quickly generate the tolerance analysis again. So let's imagine you are running a sensitivity tolerance analysis and you need to tighten some tolerances. Okay. You can tighten those select few and then rerun the sensitivity analysis. This tolerancing cache setting will dictate how OpticStudio handles the tolerances that you did not change. So if recompute all is selected, all of the cache values are ignored and everything is recomputed. If recompute change is selected, then only those tolerances that have been modified are recomputed. Results from the unmodified tolerances are just taken from the cache rather than computed. So OpticStudio will automatically clear the cache if any of the other tolerancing settings, like for example, your criterion or the sampling settings, if any of those have been changed. Okay. So when the tolerancing cache is used correctly, it can significantly speed up your analysis. Okay. But keep in mind, OpticStudio will not reset the cache if changes are made to the lens data in a given file. Okay. So the cache should only be used when no changes are being made to the lens system itself. If changes are made, you have to change the cache setting back to recompute all in the next tolerancing run. So the intention of this feature is to significantly speed up a tolerance analysis where changes are being made to the values of individual tolerances, but no other changes are being made between tolerance runs. And again, if there's ever a doubt to the validity of the cache data, set cache back to recompute all and repeat the tolerance analysis in full. So throughout a tolerance analysis, various tolerances will be relaxed or tightened depending on how they change the criteria or whether the tolerance is within budget. And this process gets repeated over and over again until we're satisfied that the system performance is within specification and that the tolerances are realistic, meaning they don't unreasonably increase the manufacturing costs. In this repetitive process of changing tolerances and then reevaluating the system performance, it's very likely that only a few tolerances will need to be adjusted each time. Okay, so it really isn't necessary to recalculate every tolerance operand over and over again. Okay, and this is why the tolerancing cache can be so important. But we can also take this a step further. We can quickly compute the criteria for tolerances which were adjusted as well. Or we can do this by fitted formula, and this leads us to polynomial sensitivity tolerancing. And the benefit here is that potentially hundreds of hours of computation time can be saved. So let's look at the Cook triplet again with another slight variation. So here, if you look at the 3D layout, it's the same Cook triplet you've been seeing. The only difference is that we have two coordinate breaks around the first lens. And these coordinate breaks can be used to decenter or tilt the first lens element. So let's say we're moving the first lens element up 0.2 millimeters in Y, and then the subsequent air thicknesses can be optimized so that we are still finding the smallest RMS spot size at the image plane. Okay. So we can do this by plugging in different values here in the decenter Y. Okay. And this will automatically be picked up and undone with the second coordinate break. And I did insert these coordinate breaks in dummy surfaces using our tilt and decenter elements tool. Okay. So all of the pickups and undos are implemented correctly. After I change the decenter in Y, I can optimize these values. And if you look in the merit function here, I just built a default RMS spot size merit function. Okay. So then I wrote a very quick macro to loop through some different decenter Y positions, okay, and optimize these parameters about 3 or 4 optimization cycles, and then to return the resulting merit function value. Okay. Okay. So I plotted the results in Excel, and you can see that the resulting merit function is a very smooth curve right here. So again, all I did was move this lens up and down 0.2 millimeters in Y, and then I adjusted the air spacings after that. So because the perturbation is small, the merit function is very smooth and has a single minimum. So over a small range of perturbations, and in tolerancing, we are only looking at perturbations on the order of manufacturing error, then the performance curve can be fit to a relatively low order polynomial. And the polynomial that we use in OpticStudio is shown here, where delta is the tolerance perturbation and P is the resulting criterion value, or you can think of it as the performance. OpticStudio lets you choose 2 different options for this polynomial fit. You can use the first 3 terms or the first 5 terms. If you choose the 3-term option, it omits the D and E terms. And it will also use 4 equally spaced points within the min and max tolerance values for the fit. Similarly, the 5-term will use all terms, and it uses 6 equally spaced points. So this plot is just showing an example of a fit using a 4th-order fit, so something that could be comparable to a 5-term fit in OpticStudio. And the beauty of this is that once we have a mathematical equation for how the criterion values or the criterion result will vary as a function of the tolerance perturbation, then all of the calculations that you do after that are almost instantaneous. So for example, if we choose to tighten the tolerance on the decenter of our first lens element, we won't need to recalculate the tolerancing criterion directly. Instead, all we need to do is plug the tolerance perturbation into our fitted polynomial equation and evaluate the new criteria. So for more information on tolerancing in OpticStudio, again, you can check out our knowledge base at zmax.com. I would highly recommend looking in the tolerancing section there for many other knowledge base articles, really ranging from introductory content to tutorials for more specific manufacturing scenarios. The help files also have a comprehensive section called Tolerancing Overview. Then the best option, if you have time, is to take one of our newly updated training courses shown here. And in summary, there are 2 main categories for accelerating your tolerance analysis. These are engineering choices and specialized OpticStudio features. So the intelligent design topics we covered were about when to use, or more specifically, when not to use, the automatic optimization setting. We talked about tricks for reducing the number of data points and that you should remove weak tolerances in the beginning. Then the tolerancing evolution was about how you can adjust your strategy as you go and start with the worst case scenarios. Then we talked about OpticStudio features built in to help you accelerate your tolerance analysis. And just as a review, you can use the paraxial focus compensation when you have very poor performance, or on the other end of the spectrum when you have very tight tolerances. And then you can use the tolerancing cache when you are changing some tolerances and not all of them, and when you're not changing any other system data. And then lastly, polynomial sensitivity can be used when you are just tightening tolerances. Okay. Thank you very much for attending this webinar. We really appreciate your support and hope that you found the content interesting. If this is your first time attending one of our webinars, please take a look at the GoToWebinar control panel. You'll see that there is a question section. So please feel free to submit any questions that you have now. I may not have time to answer all of the questions that are submitted, so if I don't get to your question, please feel free to email me at feedback@zmax.com. So with that, thank you again, and I will take your questions now.